Right, hello. Today we're going to talk about inductive reasoning, conjecture, and counterexamples. This is the first lesson in Unit 2 for geometry this year. As always, you want to make sure you write your name on your notes. And the topic, inductive reasoning, conjecture, and counterexamples. Make sure you put the date. We'll be doing this on the 21st and 22nd. And in all of the classes. All right, so for inductive reasoning, that is sort of a fancy way of saying you are making a conclusion based on observations and patterns. So you notice that the same thing's happening over and over again. You're going to make a conclusion that that is a thing that has to happen. That was not very helpful. I'm sorry. And a conjecture is your concluding statement that you reach using inductive reasoning. So a concluding statement reached using inductive reasoning. All right, so basically we're going to use some inductive reasoning to make conjectures about these numerical sequences. So the first one, we've got 38, then 31, then 24, then 17, and you might be noticing that for each of these, they've subtracted 7 from the number before it. So 38 minus 7 is 31, minus another 7 is 24, and another 7 to get to 17. So if we take off 7 again, that's 10, again is 3, negative 4, negative 11, and negative 18. So a conjecture could be to get the next term, subtract 7. Right. Then the next one, we've got 2 and 5 and 11 and 23. This pattern's not quite as obvious. So you think about it as, okay, here I added 3, here I added 6, here I added 12. It looks like the number I'm adding is doubling each time, and it's also one more than the number before it. So we could write this as, let's see, after 23, our next one would have to be 47 because we'd add 24. And then we'd add 48 to that to get 95. Add 96 to that for 191. Add 192, you get 383. And you'd add 384 to that to get 767. So a couple ways to write this. Each term, add the previous term plus 1. Or you could say that you are double the previous term and then add 1. So it's two sort of different ways to do that, to think about that, but basically we're just adding 1 more than the last term. So when it was 2, we added 3. When it was 5, we added 6. That one's a little confusing. Okay, number 3, we've got 1, 4, 9, 16. I don't know if you're noticing, but I'm noticing that these are all perfect squares. 1 is 1 squared, 2 squared, 3 squared, 4 squared. So we've got 25, 36, 49, 64, and 81. So each term is a perfect square. To find, we'll call it term n in quotation marks. N is just a letter we're going to use to refer to any given term in our sequence. You will just square it. Right? So each term is n squared. So for term 1, it's 1 squared, term 2 is 2 squared, etc. And I'll write that down so we can see. Next, it's got letters, so we're not talking about numbers as much anymore. We're looking at some letters now because you don't have to be talking about numbers to do a sequence. So we've got A, D, G, and J. So it looks like we skipped 2 letters here, we skipped 2 letters, and we skipped 2 more letters. So M, P, S, T, U, V, W, X, Y. Right? To get the next term, skip 2 letters of the alphabet. Next term, skip 2 letters of the alphabet. All right. The next one is time. So we've got 7:30 and then 7:55 and then 8:20. Let's see, that's 25 minutes apart. That's 25 minutes apart. So I'm guessing that's what we're doing every 25 minutes apart. Okay, 10 o'clock, 10:25. To get the next term, add 25 minutes. Okay. Next, we've got 3, 1, 4, 1, 5. Maybe also not as obvious, but these are the digits of pi, which is like sort of the big popular math number. So 3.141592653. Digits of pi to find the nth term, find the nth digit of pi. Right, so again, that's something you'd have to like have sort of the background knowledge for, but we'll try not to give you any that are too tricky like that. And we're just trying to like get a basic understanding of inductive reasoning and conjectures here. So that is the end of the first page. We're going to flip to the back to talk about counterexamples. So a counterexample, helps if I open the pen from the right side, is an example that shows a conjecture is false. So in this case, we're going to be looking at a conjecture that someone may have made, and we're going to be like, is this true, or is there something I can think of that proves it's false? So for the first one, the sum of any two consecutive integers is always odd, and that's actually going to be true, because if you add like 1 plus 2, that's 3, and every pair of integers has an even and an odd, and even plus an odd will always be an odd number. Okay. Next, we have the product of two numbers is always larger than either number. And that's actually going to be false because it doesn't specify that we're talking about like natural numbers like our counting numbers. We can think about fractions or 0. So 2 times 1/2, those are both numbers. It equals 1, which is not bigger than 2. Or you could say that 5 times 0, both of those are numbers. It equals 0, and that is not bigger than 5. So 2 examples that prove that wrong. There are lots more for that one, counterexamples. Okay. The product of two perfect squares is always a perfect square. And this is actually also true. So, fun fact about perfect squares. All right, next is if the area of a rectangle is 6 meters squared, then the dimensions must be 2 meters by 3 meters. And that one is actually going to be false because the area of a rectangle is just going to be the length times the width. And 2 times 3 is not the only way to make 6 with multiplication. 6 meters by 1 meter also equals 6 meters squared. So that would be just like a long skinny rectangle. Like that. 6 meters, 1 meter. Okay. Next is dividing by 2 always results in a number less than the original number. So again, because it's just talking about numbers, this one's going to be false. You'd have to be more specific about what kind of numbers you're talking about for that. But if you divide like a negative number by 2, a positive 2, you'll get a negative number that is a higher, bigger on the number line than what you started with. Or of course, if you divide 0 by 2, you'll get 0, which is not less than 0, it is equal to 0. So negative 4 is actually greater than negative 8, and 0 is obviously equal to 0. So that one is false. Number 12 says vertical angles are never complementary angles, and we just learned those ones. Remember, our vertical angles are the guys that are across from each other. Complementary means that they add up to 90. So this is also a false. Okay, because these are equal. You have the possibility of having 45-degree vertical angles where they're both 45 degrees. And that means that they are complementary. Next is if A times B equals 0, then either A equals 0 or B equals 0. And that one's going to be true. If you multiply any number by 0, you get 0. And the only way to get 0 from multiplication is by multiplying by one of the numbers being 0. So that one's true. Right? Next is two angles that are supplementary to the same angle have to be congruent. So if I had like this angle, 60, and a 120, and I know that this angle and this angle are supplementary, this angle and this angle are supplementary. Well, if this one's 60 and this one's got to be supplementary, it also has to be 120, and that will work for any numbers that make supplementary. So that is a true statement. Okay. Number 15, all state names, like the United States, have at least 2 syllables, and that one is false. Maine has only one. I think that might be the only one that's only one, but I could be wrong. But just one example is enough to prove something wrong. Okay. Squaring a number and adding 1 will always result in an even number. That one's going to be false, because if you square a number and get an even number out of it, then add 1, it makes it an odd number. So like 10 squared is 100, 100 plus 1 is 101. That's odd. Same thing if you were doing like 8 squared. 8 squared is 64, so plus 1 makes it 65, which is odd and not even. And that's the end of those notes, so I'm gonna, nope, where am I? Okay, end that, and I'll see you in class.